Sim, sim. 2 minutes. Or is everybody here? I don't know. 2, 3, 4, 5, 9, 13, 15, 18, 21, 25, 28. Faltam 3 ainda. Você ou posso eu ter pulado? Okay. Hello. So first, I want to say something about tomorrow. Tomorrow, we won't have a normal class. I won't teach on the blackboard as they do. Tomorrow is session for questions and discussions. So you have to make questions. So think about questions. Questions can be doubts about the things that we discussed, or just raise comments, whatever. Everything is allowed. And then there is a second point, is some of you maybe don't want to pose the question because you think, oh, probably this is too elementary, I don't know, and so on. So you can write down your question and put it on a box. Okay? And you sign if you want, or you don't sign if you want. So you get the answer to your questions anyhow. Okay? So do it as you want. If you want just to raise your hand and pose the question, or write down the question. Sometimes it's a longer question with some mathematical formula, so it's better to write it down, and so on and so on. Okay? So we will do this tomorrow, and it's also a way not to have too much new things one after the other. Okay. So, in the previous classes, we have discussed single species dynamics, and we will move to interaction between species only on Monday. Today, I will talk about still single species, but in a different setting, which goes under the name of discrete time dynamics. And so, okay, first of all, what is discrete? Discrete in this case is there to say the following: that usually the time runs, so the time is a real number. Okay. So if you go the evolution in time of a function, then time goes on continuously as a sequence of real numbers. Now, discrete time is when the time is not continuous, and it actually will be an integer, right? So time equal to 1, to 2, 3, 4, 5, 6, 7. So there's a certain time interval, and the other when you between, say, time 1, time now, and the next time could be 1 hour, or 1 day, or 1 year. And then I will have the function has only values for 2 times this one, 3 times, 4 times, 5 times. So this is means discrete, Okay? You have seen discrete distributions with what Andrea in the second class told you about. You have probability distributions like binomial and so on. It has only some points. It's not a continuous line. Whereas you can also have continuous time, then you have the probability densities, right? So pretty much the same thing here. We will now discuss dynamics when the time is a discrete number. A discrete number means integer number. That's kind of jargon, so, okay? Okay. Now, why? So, there are many instances where discrete time dynamics could be interesting from the ecological or biological point of view. And the most preeminent case is when you have species that have generations that don't overlap. Okay, so this is very common with insects. Okay, so you have a generation, and you have the individuals of this generation, they oviposit, they lay eggs, and then, well, this insects die, and the next generation will emerge only later. So I have one generation, then I have the second generation, and the third generation, and the fourth generation, and so on. Okay? And this is clearly a case when, how would you describe this in continuous time, okay? The population n with continuous time, it would be a certain population here, and then it dies. And then comes a second population here, and then it dies, and then third population here, and it dies. Maybe that's so the ever can have a dynamics, but it is much easier to study this and saying how many I have here, 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 and here. Okay? So this is a way. It's much more simple to study this dynamics by looking at the size of the generation, and you maybe, if this is not instantaneous, you can define maximum population or something. But you look only at time 0, 1, 2, 3, 4. 1 what? Generational time. 2 generations, 3 generational times, 4 generational times. So it's much easier, okay, to look at this way than trying to find a differential equation that will have this behavior, which is much more difficult, okay? So this is a, there's no erasing. Here. This is a case where clearly it is more interesting to have the time being counted by generations, okay, instead of being a real number. But there are also situations which are not connected to necessarily to generational time, when you have a population dynamics in continuous time that has peaks, for instance, and you measure only, because you go to the field, you can measure only the peaks. For instance, if I have a complicated dynamics over time of a certain population which goes up, down, does a lot of things, so on, maybe I cannot measure all the time. So maybe I can only measure from time to time. So maybe I can think I will only measure the peaks, okay? So even it's not a thing connected to the generation, it is a way, this could be closer to what people can observe. Obviously, you are losing all the information in between, right? So continuous time has much more information in the sense. But sometimes it's not even realistic to think that you can measure things continuously, And then you can say, maybe I just want to measure the maximum values of these guys, and that's enough for me to understand the dynamics. So I have a small, I mean, it's less information, but maybe this is also already something which is interesting and which is simpler than the whole model. Okay. For instance, when I talked about the generations with insects, which go up, down, and so on, remember, with the single species dynamics that we discussed, there were no oscillations. So that could not be described by a single species dynamics as we did with differential equations in this case. Okay? There is a way, but this involves time delays. Okay? But that's not the topic here. Okay? Well, okay. So how would you formulate discrete time dynamics? So I will call the population size x. Okay, that's very common. I could call it n again, but sometimes people make confusion. The n is the continuous, so I will call x. And instead of writing x of t, I write x of t like this. Okay. Okay. It's just a notation. That's the common notation in when you do discrete time dynamics. So the idea is that this means that this will be this. People look at this and say, "Oh, it's discrete." Okay. So we have x of t, and then say, so x of t will be what? Will be x of time 0, x of time 1, x of time 2, x of time 3, x of time 4. Okay. 1, 2, 3, what? Units of time. Whatever unit you use. Can be generational time, could just be years or months or whatever. Okay? So, this is how this function, what this function means. And now, to describe the changes over time of the size of the population, I have to write, say, x of t plus 1 equal to something which is connected to x at time t. So the idea is that the generation at time t will give rise to a new generation or a population at time t plus 1. Okay? So that the population at time t plus 1 is just a function of the population of time t. Okay? So, what's the simplest thing that you can think about? The simplest thing is just say, this is a linear function. Now, this r is not the same r as before. Okay? Here's discrete time. This r has no dimensions. Because you have a dimension of population here, dimension of population here. You don't have a derivative, okay? Then this has no dimensions, okay? So it's not like the other r. So what does it mean? You could also think that x of time t plus 1 is the population at time x of t plus x plus the population change from time t to, so the population change would be some lambda x of t, okay? And then you would say this is just x of t times lambda plus 1, and lambda plus 1 I call L, okay? So either way. So now, let's think about R. First thing. So this is This is the simplest model. And guess what? What's the name of this model? Malthus model. Because actually this is Malthus model in discrete time. Okay, so this is Malthus. So, first of all, so the population of at time t gives rise to a new population at time t plus 1 with a factor r. If r is smaller than 1, that means the population is decreasing. And at every time step, it will go on and decrease and decrease and decrease. Therefore, it goes to 0. And therefore, r smaller than 1 means the population is decreasing and it goes extinct. So there's no fun with r smaller than 1. Okay? Now, if r is bigger than 1, then it's increasing at every time step. Okay? So I go from population at time 0 to a population at time 1 that is bigger than the population at 0. And the population at time 2 is the population at time 1 times a factor, which is also bigger than 1, therefore it's increasing. Okay? So this means that the population is increasing in time, and there's no bound, because it's just going on. So this is going to increase all the time. Okay? The idea here is always that this dynamics, how do you calculate the dynamics? Okay? How do you calculate the values of x at a certain time? So first, you start with x0. Then you have x1, which is just r times x0 by the equation. Now x2 is r times x1, okay, which is just r squared x0. Okay? x3 is what? It's r times x2, which is r times squared x1, which is r to the third x0. And so on. So it's easy to see that at the time any time t, this is just r to the power t x0. Are you okay with that? This is called an iteration. Iterating function. Yeah. Where's the mic?
Tem uma coisa que você falou lá no começo que... it's in English.
Yeah, well, I mean, as you prefer.
Okay. There's... okay, the R has no dimension. I did not get that.
It's just
what does that mean?
That means that it has no units. It's just a factor, a number. Usually, for instance, in the equations of the Malthus law in here, dn dt, what we discussed the other classes, the units of this side have to be the same units at that side. If you have something which has units of time or whatever, it could be more complicated, time, space, or whatever, has some units here, they have to have the same units here. Okay? So here you have population divided by time. Okay? Therefore, here you have the n, which is population. And in order to this here to be equal to this one here, then r, the units of r, have to be 1 over time in order to r times n be population over time. So it has units. This r has units. 1 over seconds, 1 over hours, and so on. And then in the first class we showed that actually 1 over r times logarithm of 2 was the doubling time of the population. Okay? So that has units. Now here, on this side, I have population, and I also have population here. Therefore, r is a multiplicative factor, which has no unit. It's just a number. Okay?
In that case, we can call R the rate of reproduction, right?
Yes, reproductive rate, yeah.
So I understand a rate is something over time.
Yeah,
But
in this case,
I cannot see the same thing in this R
it is
discrete time.
well, it is not a rate. It's a multiplicative factor which says from time 1 to the time 2, I have a certain increase or decrease of population, which is some constant factor. In this simple model, it's a constant factor. Okay? So say r is equal to 2, just to make it simple. So at time 1, I have 2 times x0. At time 2, I have x2, which is equal to 2 times x1, which is equal to 2 to the squared x0, and so on. So it's just a multiplicative factor from one generation to the next. Okay? So, okay. Now, and this comes from the fact that it's discrete and I don't have the derivatives, okay? If I had the derivative like here, then I have it divided by time, okay? But here, I don't have anything like a division by time, okay? It's just a multiplication from one time to the next one. So, I'm pretty sure that in the high school you had seen this thing, which is, this is just a geometric progression. Right? That's called a geometric progression. I think most of you have seen this. And I don't know how people call this R in geometric progression. It's just the step, okay? So this is the simplest model, which says that over time, population will increase indefinitely. Go on, forever. So this here is analogous to the exponential growth in time. Okay? In this case, obviously, time here is discrete, but you can see that it's also, it's a power of t. Therefore, I could just rearrange these things and write it as an exponential. Okay? So it's exponential growth in time. Again, Malthus and all the stories that we have discussed in the first class. So, okay. So now, we want to have something better than exponential growth. And maybe the first idea that comes to your mind, I'll say, okay, let's proceed in a way such that if the population increases to match the growth rate, the R, will somehow be smaller. So it is like if you had a geometric progression, but the step from one time to the next one depends on the size of the population. Right? So the simple thing that people did, and people also do, was, okay, let's try this. So let's modify this with something which, when x is small, then small x against 1, it's not important. And x is close to 1, this is important, and this has a negative, this x comes with a negative sign, therefore this x, for large populations, the growth will be smaller than for small populations. It's the same thing that we did with the logistic equation in the last class. So then maybe you are looking at this a little bit like, where's gone k? Isn't there a k there? A carrying capacity in this case, you could think about that. So, okay, I want to ask you to accept not to have the k, because that's the following. I can always scale out the k. What means scale out? Say I had put this here, okay? Then I can just call this y. Okay? I call it y. And then I change to y here, and will be the same, okay? So if you want, you could call x over t, okay, y of t, then x of t will be y of t times k, then you have y of t plus 1 times k is equal to r k times x y of t times 1 minus y of t. So this cancels, and you get the same equation without the k. Okay? So you can always scale out the carrying capacity by changing the way you measure the populations. Okay? So usually you would say, I have a population of 10 individuals, but say the carrying capacity is 10. And I can say, I have 0. Say you have individuals. Say you have 2 individuals. Then you have just 0.2 carrying capacities. Okay? So you can measure in not only with individual by individual, but you can say how many units of 10 or how many units of the carrying capacity do I have. Okay? You and then you.
So just to be clear, on the first equation without the k, x of t can never be bigger than 1, right?
No, it can be, because you will see it can actually, because okay, in principle it could be. It gives you a negative population, okay? So this is a problem of the model, actually. That's a problem of the model, yeah. We will always have be between 0 and 1, okay? But the reason is a mathematical. It's not because of carrying capacities. Because actually, if I put a k here, that's not really a carrying capacities, because the population won't go to k, okay? So I'm just saying this because I will just make it disappear from here, okay? So we don't have the parameter k, which simplifies the problem because we have only one parameter, which is the r, not the r and k. Okay? So there was another question here? No? Okay. Yeah. So actually, okay. So x has to be smaller than 1. In order to make sense from the biological point of view, it could be, I mean, give you a negative number. Well, negative number exists mathematically, but it's obviously there's no such thing as a negative population. Okay? Okay, so this is what we want. We want now to look at this and say, maybe this is better than this one. With the differential equation, this worked fine. Right? So we get increase, saturation, and then we are happy, and that was it with the logarithm, with the logistic equation. So now the question, what happens with this one? Okay? That's the question. Okay? So I will discuss qualitatively this, and then I will show you computer simulations. okay? Because this is clearly something which is very easy to put into a computer. It's just a loop, okay? You have seen loops with the other, I don't know, Renato or Paulo. Okay, so it's just a loop. I have a value, I get the next value, and I get the next value, and the next value, and the next value. So it's very easy to write a Python or R program of a few lines that will give you this. Okay, it's very easy. So I will show this because I will need to make it computational at a certain point. But before, we will make a plot of x of t plus 1 against x of t. Here is the 0. Here is the 1. I will put it in yellow. So x of t plus 1 as a function of x of t is again a parabola. The same parabolas that we had before. A parabola that increases, more or less, here. Let me put a point here. So I'm not very good with drawing things. And which decreases, okay? So, how would we solve graphically this equation? I have to start with some time, population at a certain initial time, x0. Say it is here. This is x0. How do I obtain x1? I look here, and I get the x1 here. So this is x1. Now, how do I obtain x2? Well, I have to put the x1 here. Okay? So I measure this. I put it more or less here, let's say, x1. And then I get here, and I get x2. Then I have to take this value x2 and put it on this axis and go on forever with this. So there's a way to do this a little bit easier, which is drawing an auxiliary line. So let me put all of this back. I will draw we only have yellow here. An auxiliary line, which is the line that is the line x t plus 1 equal to x of t. Okay? So this is something maybe like this. Okay? This is meant to be a straight line, although it's not so straight as it should be here. Okay? It's a straight line. What do I do with the straight line? It will help me to switch from this value back to this one. So again, I start with x0. I get x1. Now, if I want x1 on this axis here, I just have to take this. Okay? Because this is the line that takes xt plus 1 equal to xt. Okay? So it's the identity. So if I do this, I project from here to here, then I'm okay here. Now I can go for x2, which happens to be here, and project it here, and get here x2. Then I go here, and I project this to x3. And then I project this here, x3. Right? So this is called cobwebbing. Okay, so this is a graphical way to look at this equation. So, question.
Sorry, I have quite a basic question from before. I didn't understand very well how that 1 minus xt appeared in the equation. I understood the whole graphic explanation,
Yeah.
though. I just didn't understand that part.
This is a tentative way of avoiding exponential growth forever. So if I want to avoid exponential growth forever, in the same way as we did with the logistic equation, we have to have some mechanism such that populations that are large will have a growth rate smaller than populations that are small. So the idea is that there's interspecific competition again. Okay? So this is a mathematical way to construct, to build something like that. So if x is between 0 and 1 in this case, okay? So if x is small, like 0.1, then this here has almost this has almost no effect because it's 1 minus something which is smaller. Okay, so it has almost no effect, and then you have the exponential growth going on. But as the population increases, this one starts to come near to the value 1. And then this here is something like a smaller number, so a 1 minus 0.9 is 0.1. Therefore, the effective increase factor will be r times 0.1, which is 10 times less than when the population is small.
I see. So in this equation, xt will always vary from 0 to 1.
Yeah.
In that equation.
Yeah, that's
Okay.
that's because because of the small discussion that I have already erased. It is you can measure a population not only in 1 individual, 2 individuals, 3 individuals. You can measure in other units of 1,000 individuals, for instance. Okay, if I have 10 individuals, I have 10 over 1,000 times 1,000 individuals. Okay, so we can measure not only in the unit 1, we can measure in the units we want. So I'm measuring this, saying that the maximum population is 1, but it's not 1 individual. It's 1 times my population scale that that's implicit here. Okay? Yeah. Okay. We continue.
Sorry. But let me say, 1 would be the maximum number. 1 would be the maximum number of a
Effectively,
population.
yes. Yeah.
Oh, I see. Okay, I get it.
I mean, when we discuss this graphical on the computer, you will see, in principle, mathematically, there's nothing that says that you could have x bigger than 1. But biologically, this cannot be, because x bigger than 1 makes this a negative number. Therefore, it creates a population which is negative, which is nonsense. Okay, so that's a restriction. It's not a mathematical restriction because negative numbers are negative numbers, but it's a restriction in the sense that it's nonsense biologically. Okay? But indeed, this is a problem from this model. I will show you at the end of the class, there are models where you don't have this problem. Okay, because that's the fact that this is a simple model, because it's just a parabola. But there are other models that are more complicated, have exponentials and so on, but then they don't have this kind of problem with negative populations. Okay, which are the models that are effectively used in practice. Okay?
Well, I was trying to make sense of this 1 as the maximum value before you started explaining.
Yeah.
And I was interpreting it as a proportion.
Yeah.
Like 1 is the K, the carrying capacity, where the population reaches 100% of the number of individuals the population can have.
It did not reach okay, let us call reference population, not carrying capacity, because this is not the differential equation. And actually, if I put a k here, the dynamics will not go to k, it goes to something else. Okay? And this won't reach 1. Okay, don't. So I will show you in just a minute. Okay, so so let's call something a reference population. That would be the K, but it's not carrying capacity. Okay, but I say reference population is 1,000, 100. 100 individuals is the reference population. Okay, and I have a population with 10 individuals. Okay, so I have 0.1 reference populations. Okay, I have 50 individuals. I have 0.5 reference populations. Okay, instead of counting individual by individual, we are counting them by hundreds. How many 100 individuals I have? Okay, I have 0.5 hundred individuals. Okay, so I can count individuals in groups. How many groups of 100 I have? So I have 0.5 groups of 100. Okay, so that's the reference population. Okay, so I can do this all the time. And here, what I'm doing is just, as I said, I could have a K here, but this can be scaled out mathematically. Okay, by thinking that we are counting in the reference populations. Okay. So, but it's not the carrying capacity, because why? Okay, so the first thing you could ask yourself is, okay, is there a fixed point? Remember, the carrying capacity was the fixed point of the logistic equation. Okay? Now, what is fixed point here? It's the point x of t equal to x t. This is fixed point. If you get a time t plus 1 is the same value, and it stays for always the same value. So that's the fixed point in this case. So if you put this here, then you substitute this here. Then you cancel here. Then you have 1 equal to 1 over r equal to 1 minus xt. I would put xt star in the sense that that's the value of the fixed point. Okay? Not so x star t is 1 minus 1 over r. Okay? So that's the fixed point. So the fixed point is not 1. You could say, this is a carrying capacity of 1. The fixed point is not 1. It depends on r. So it's completely different. Okay? That's the point. It's completely different from the fixed point of the logistic equation. Okay? Okay, but let me still do some cobwebbing, but let me erase this one because it was not very well suited. And again, let's do this plot. Let me draw a straight line. And now, if you look at this, the parabola is always something which goes to 0 and 1. But for different r's, I have different parabolas, okay? So if r is super large, then it will be steep parabola. Okay, we'll go up and so on. But then if r is not so large, then we'll have another kind of parabolas and so on. So let's try one which is not very steep. No, that's not good. more or less like this, and do the cobwebbing. Okay. So now, I start at x0. I go here, here, here. Okay, x0 gives you x1. x1 projected on the side, it's x1 here. I can get this x2 here. I project x2 on the line. I get x2 here, x2, I get x3, which I project here, and x3 I get here, which gives you x4, and x4 I project here, which is x3, x4, and this is approaching this point. Okay? What is this point? That's the point where xt plus 1 is equal to xt, because it's a straight line of inclination 1. Okay? That's the fixed point. So when the parabola crosses the fixed point, the straight line, that's the fixed point. Okay? Now, in this example, this got on increasing, and get into the fixed point. So that's pretty much like the behavior we had with the logistic equation, where we just had increase and then going to some constant value, and that's the same thing here. Now, I told you this behavior can depend on the steepness of the parabola here. So let us try with a parabola that starts steeper here. Okay, so let me draw this here. So remember that fixed points are only relevant if what? If they are stable. If they are not stable, they are not relevant from the observational point of view for anything. Now, we have found a fixed point, and the convergence was pretty much okay. So now let us do the same exercise with a steeper parabola, like this. And do the same thing. I start with x0. I calculate x1. Sorry. x1. x1 I project it here in order to calculate x2. Then I project it here. And I calculate x3. So it happens that x3 actually is smaller than x2. And then I project this here, and I get x3 here. And I go there, and I find a value for x4, which is very, in this case, happens to be very close to x4, which is here. I project it here. I will get it here. And when I project this one here, it will be smaller again. So that you have oscillations. Okay? You have oscillations. So if you want to call this the fixed point, the carrying capacity, okay? You can do it, because it was pretty much what happened with the carrying capacity in the continuous time. Now here, you have the population goes increasing and overshoots the carrying capacity. And then it gets back below the carrying capacity, and then gets overshooting again. So it gets from one to the other. Therefore, this fixed point actually is unstable, okay? If anyway I start here, I will go on oscillating, not going back to the fixed point. So the fixed point is unstable, but you get a population that goes up and down in time. So this is very different from what you had with the logistic equation in the continuous time. Very different. You didn't have any overshooting, we didn't have any oscillation, and here we have. Okay? So this is compatible with the continuous time if we think that actually we have a time delay, because I'm saying the population at time t plus 1 depends on time t. So there's a delay in the equation, but it's a kind of disguised delay. Okay, in the continuous time would be a delay, and then with delay in continuous time differential equations you can have oscillations.
In the first graph, we have a fixed point that is stable.
Yep.
And the second, it is unstable and goes back and forth.
Exactly. So now, instead of having me drawing things, and I'm not good at drawing, let us do it now, not graphically, but computationally, okay? Which is very easy. So just give me 1 minute, because I don't want with my hands to just a minute, I'm come back. I want to wash my hands. Okay, so there was a question. There was a question, yes? Somebody raised it. No question anymore. So, okay, let's go on. So, please attention, people. So, I see that you are not paying attention anymore. So please, if you don't pay, you won't understand anything. Okay? So, okay, okay. Please don't talk so loud. And okay, so this is a small Python program, which I won't discuss the programming. Okay? And actually, Renato will show you this program, not this program, but it will solve the logistic. Okay, this I didn't say that the name of this, so some jargon here. This discrete time dynamics is called in mathematics. It's a map. Okay, so it's called a map, and this is called logistic map. So don't make a confusion between logistic equation, which is something which has had to do with the continuous time, and with the logistic map. Okay, the logistic map is this one. So Renato will actually show you how to write a code to solve the logistic map. Solve means obtaining x1, 2, 3, 4, 5, etc. Okay. So this is a small piece of code here. You have actually the equation is r times x, 1 minus x. Maybe, let me see if I can. Is it better this way? Yeah. Yeah. You. I can zoom. It will not be practical because my plots will be always at the end. Okay, but you can you read it? I mean, you don't need actually to read the code now, okay?
I have a definition question. Why an oscillating point is called unstable if it comes back to
No,
To
the
the
oscillating point is not called unstable. The fixed point here is unstable, and the trajectory is
an
oscillating.
Okay.
Yeah, it's easy to see if you start near this fixed point, instead of going back to the fixed point, you start to oscillate. Okay. Therefore, the fixed point is unstable.
Because it's not an attractor.
It's not an attractor.
Okay.
Okay.
Yeah, thanks.
Yeah, but we have. I will show you in a minute. We have different fixed points, which will be called cycles in a moment. Okay. So this is a Python code that iterates this function here. Okay. And it calculates what in mathematics we call these trajectories. Okay, the function x of t, which are solutions to equations or to maps, orbits. Okay, so just if you hear the word orbit, it's just a trajectory, which is just the time evolution of the function x of t. So this logistic equation here needs an initial condition, which is called the seed, okay? Something between 0 and 1. Then you need to give r as an entry to this function. Then you say how many time steps you want to iterate, okay? And then you can also say, I want to iterate a certain number of steps, but first I iterate, I want not to plot the function from the time 0. I want only to plot the function after some times. Why? Because I want to go to the attractors, asymptotic dynamics. Therefore, I don't want to see in many cases, I don't want to see the transient. I want to go directly to attractors and take some time. So it can be easier just to iterate over 1,000 and plot the last 100. That's what is written here. Okay? But at the first example, we will not skip anything. Okay? So I will just make this a little bit smaller. Oh no, how do I make it smaller? No idea. No. Okay, so can't make it smaller. So I will always use a seed of 0.1. Now, you could have asked, well, what you did here could depend on the initial condition. Okay, that could be. Maybe if I start with a different initial condition, I get another different point. But actually, this is not the case for this logistic map. Anywhere you start, after some time, you get to the same attractor, either fixed point or oscillating things. Okay. So I would put r equal to 2. Okay, not 2, 1.5. Let's start with 1.5. And iterate it 100 times. Yeah.
Just to follow you, what does the seed of 0.1 means biologically? Just to follow you, what does the seed of 0.1 means biologically for our population?
Means it's the initial
the initial population.
Initial populations.
Okay.
Initial population related to the reference population that has between 0 and 1. Okay.
Yeah. Thank you.
So, and run it, and you see the solution is pretty much what we expect. So I used 1.5. The solution increases and goes to a fixed point. Nice. It's not the same form as the logistic curve from the logistic equation, but it's actually, it increases and goes to the fixed point. Okay? And if you want to be convinced, you can also look at this with another seed. Let's say okay, a seed of 0.8, then you go there, and it drops and goes to the fixed point. Okay? So, let's go back to 0.1, and let's increase R. So increasing R is increasing the steepness of the parabola. Small r's are like this. Big r's are like this. Okay? So let's play the game of increasing R. Okay? That's nice. Let's put 2.5 and run. So you got another, again, a fixed point, but you know, there's some ripples here. There's some ripples. What are these ripples doing, okay? So let's see what happens if you increase a little bit more. We go to 2.8 and run it. We get oscillations. So what these oscillations mean? I'm at a certain time here. I go to a big value, a larger value than the first one. Then I go down and then go again up. The population size is oscillating, going up and down. But the oscillations decrease in time. And decreasing in time means that they are approaching again the fixed point. But before you get to the fixed point, you have oscillations. So these are transient oscillations. Okay? So if I, for instance, skipped here, I skipped the first 1,000 iterations, and I only plot 100 oscillations after 1,000. Then you will not see the ripples, okay? Because they have been already damped, okay? Damped out. So that's a kind of what in physics is called a damped oscillation. So you don't see it, okay? So the fixed point is there. But there was actually something interesting in the transient, in the sense that you have oscillations, but they are only transient. Okay, and these oscillations will increase if I increase this even more. Yeah.
Can from the equation we think about upper limit for R?
For R,
Yes.
there will be an upper limit for R.
But
yeah.
from the equation is not.
For the time being, there's that. I mean, there is an upper limit for R to such that this equation can be biologically meaningful.
Yes.
But if R is bigger than 4, actually you get negative numbers.
Yeah, that's what I read. But why 4?
Not why 4. I mean, it's a consequence of the equation. It's a mathematical fact. Okay.
But you said to be biologically meaningful is
The
represent a real
to represent a population cannot be negative. Therefore, if you have a dynamics that takes you to negative populations, there's something wrong with your model. Any meaningful model has to have positive population. So that's also very useful for your group exercises and group projects. If you write down a model and it has a negative population, you better change the model. Okay, so this model, it's a kind of paradigm of maps, but you have to take care that x is between 0 and 1 and r is between 0 and 4. Okay. So, but the point is, you see, you get this kind of overshooting here and undershooting if you want, and then over time this disappears and you get to the fixed point. So now, let's say I want to increase this more. So the next idea would be to put it on 3. But I will put it on 3.1 because on 3 is a very special point. Okay, so why? Okay, it is a bifurcation point, and the transient goes to infinity. So it's better to have something which is not exactly 3. It's like the transient being going. You are always in the transient. Okay. So let's put 3.1. And then you see suddenly that you have the oscillations. Population goes up and down. But it is not disappearing. And say, okay, maybe if I go and plot for a longer time, I have only plot for hundreds, then I say, okay, let us calculate 1,000 steps and then calculate the next 100 steps and see if after 1,000 and 100 steps the population is still oscillating or is it not oscillating, okay? So there it is. It is oscillating between 2 points, 2 values, okay? This is the case that we would have here when you go from up, down, okay? So, yeah. Where Mike.
If you say R is 3, it's the first example, the first graph.
If R is 3, no. This graph is I don't have even a noun. This is something I just made it up here. I don't know the R here. It's just I was just discussing that a small r, which means the parabola is like this, has different properties of the dynamics, have different properties of a steep thing, like this one, okay? Now, I use 3.1 because I'm a smart guy, because you had a dynamics was fixed points. When I crossed from 1, r equal to 1, when I go to r equal to 2, I have what is called a bifurcation, and I go to oscillations that decay to a fixed point. And r is 3. Then what you get is oscillations, okay, that should decay to a fixed point or not. The 3 is very special. And it takes a very long time to stabilize the dynamics. It's like a super long transient. And we are interested in the fixed points, which is what we see in nature usually. So the transient dynamics is so long with 3.0 that I just used a little bit larger than 3. I could have used 3.01 if you want, okay? And you see, you have the oscillations. Now if I put 3.0 and I don't have this, then what I would get, still, this looks like damping. Okay? Decaying, but actually if let's skip 1,000, then you go this, and it's not clear if it's still decaying or not. It's getting small. Okay? So this is a singular point. That's why I didn't plot it with r equal to 3, because you cannot inspect this by visually and be sure that it's decaying or not. So I use a little bit a bigger value, okay? So now, this situation here, you have oscillations. So it means that actually this plot, I mean, this is a fantasy plot because it draws the lines, okay? But you only have the points, okay? Actually, that's what also Paul and was explained the other day. But here it puts the lines as if the time were continuous, but it's not. Okay, so this is the dynamics that is just like that. You have a certain value here, then a certain value here, then you go back here, then you go back here, then you go back here, you go back here, you go back here. So this means that you are oscillating. Periodically, you go from one point, and after 2 time steps, you get back to the same value of x. Okay? So I go from one point to another point, and then I go back to the first. So it's called a 2 cycle. A cycle of cycle of period 2. Okay? So cycle of period 2 is oscillations, sustained oscillations in the population. Right? Let's describe a population that are oscillating. Yeah. Where's the mic? Okay.
I wanted to ask these oscillations, what does it mean biologically? Does something like that even exists in nature?
In nature, there exists oscillations. There are populations that have cycles.
No, yeah. Cycles, like exact cycles, like that. Maybe not so much.
Everything is under perturbation all the time. But there are populations that are well described by cycles. And it's usually, it's an interesting scientific problem, is what are the mechanisms that make population cycle? There are papers on that discussion. What are the mechanisms such that you have cycles in nature? So this here is the discrete time cycles, which have to do with the fact that the population at time t plus 1 is a function of a previous time, which is different from our differential equations, where the change of the population is instantaneous. Okay, dn dt at time t is a function of n at time t, the same time t. Where here, the function at t plus 1 is a function of a previous time. Okay? That's the meaning of that's what's behind this kind of oscillations. Other kinds of oscillations are cycles that exist, are induced by the oscillating environment. For instance, seasons. This make population cycle. Population increase and decrease. And the other mechanism, which is something we'll discuss next week, is predator-prey relations may show cycles. And that's observable. It is easier to observe in the lab because you can control a little bit the disturbances. The point is that in the field, you don't get exact oscillations like that because they are under perturbations. Okay?
In the Malthusian model, I understand that R influences a lot the behavior, so it's more clear what it's doing. But in the other one that we're analyzing now, if R is smaller than 1, I don't see why that would not be possible. But at the same time, it gives you a fixed point that's smaller than 0, which also doesn't make sense.
So let's put it here and see what happens with R.
Thank you.
0.5. Okay? So, this fixed point exists only if R is bigger than 1. Yeah. But I mean, the equation makes sense with any R, okay? So let it put here 0.5. And let it make a better here, like a seed which is like 0.5. It decays to 0. Extinction. Okay? Yeah, next question. So I will have to speed up because I still have a lot of things to say to show you. Okay.
Okay, just yes. If it's smaller than 1, it goes to 0. If it's between 1 and 3, it stabilizes. But when it's 3, it
gets
oscillates, but the oscillations get smaller.
No, if it's bigger than 3, then the oscillations don't get smaller.
No, if it is equal to 0, to 3.
3 is a transition point.
Okay.
Okay. So it is oscillating, kind of forever, but it's not clear if the pop of it is decreasing or not. Okay. So it's these transition points are special because they have super infinite time transients. Therefore, that's why I didn't plot 3. Okay. And then you also should notice that things that only happen for exact values of parameters in any modeling are called non-generic properties. Because if you have something that, say, you have a model that in a certain property of the model, say oscillation, extinction, or whatever, only happen if the temperature is equal to 20.1 degrees Celsius. So this is something which is not relevant because temperatures is never, you don't have exact values for things as you have already learned with Paolo and Ray and so on. The exact values, things that happen only at one exact value of the parameter are non-generic. So they are usually not observable.
And the final thing, you said that if R is greater than 4, this goes to negative, but can we see that in this code?
I can, but I have to go on, because there's still another thing will happen. It's not the end of the game here. So let me plot now 3.3, and if I point 3.3, okay. So I have a transient, and I go to stabilized. Again, the same story. Okay, let's increase. But you know, these oscillations are getting bigger and bigger. Amplitude is big. So it's oscillating every time more and more. So let us get to 3.5, 4, 8. Let's try this one, okay? So why I'm using this one? Because I already know that things happen there are interesting. Otherwise, I would have to go testing this hours, okay? So what you get here is oscillations, but they are different. Okay, what's happening with this? Let me use the pointer here. So when you are in the transient here is over, you are here. Then you get down here. Then you get to a smaller value here. And then you get down here. And then you get back to the initial one. So it takes 4 time steps, not 2 time steps, in order to get back to the initial value. And that's called a cycle of period 4. Okay? So, let me see. And then you can go on with this. Let us eliminate 100 points here. And you still have this. Okay? Now, what happens is if you go further and further, you will have where is the okay. No. If you go further and further, it is difficult to see visually because there's the size of the pixels. Okay? But you will have period 4, and then after some values of R, you get period 8. and then the period 8 goes to period 16, and then to period 32, and higher periods, all of them powers of 2. So this is a period doubling situation. It's called a period doubling bifurcation, actually. Not to 4. Good question. Then you would say, okay, can you go on with this forever? Will it double? I mean, will it double forever? And the point is that there's a certain value, which I forgot to take note, but such that the period goes to infinity, which is 3 point something. I should have taken, I didn't pay attention, and I forgot to. And so they have an infinite period. That means that it's not actually periodic anymore. Okay, because the infinite period never comes back to the initial point, therefore it's not even more periodic. And it has bifurcated, and this is for a value which is between 1 and 4. It's 3 point something. And that's when you run in this, and if you increase still more the parameter, you still get this kind of oscillations that are that have no period. Okay, so these oscillations that have no period are called chaotic oscillations, and to say that you are in a chaotic regime. Okay, so I put my, where did I put my chalk? Here. So this is chaotic oscillations. Okay, so how do they look? Well, let me try here by try. So let me put. Okay.
3.56995.
Okay, so if I put 3.6, I think it should run. Yeah. Okay. So here, you had something which has the appearance was 3.56. Yeah. So 3.6 is it's bigger, and this is actually a case where you see you have irregular oscillations. So they go up and down, okay, and they are limited between some values, but the dynamic of the population never goes back to the initial value. Okay. So I could also say, okay, let me try to see what happens. I have plotted this from time 100 and 100 more, from 100 to 200. Let us put 1,000 here. Okay. So after 1,000 steps, I plot the next 100. So you see, it is still oscillating, but you see that you have regions where it's pretty much regular. And then it gets spoiled. I mean, then it gets again irregular. So you have islands of regularity between irregular behavior. Okay, so you can go on playing with that. We could also make, let's say, okay, let's put it 2,000 here, see? Okay, so you see, it goes up and down, but it's not periodic. If I increase more, 3.8, let's see what happens. I hope that's not a curious thing, okay? So it gets weird, okay? So this is chaotic dynamics of a population, okay? So, and you see if I change the region that I'm plotting, I'm plotting now from time 1,000, you get different things. So it's really irregular, okay? So, first thing this is irregular, and many things in nature are irregular. But this model is deterministic. It's not a stochastic model, it's deterministic. And it shows you irregular behavior. That's the point that caught a lot of attention and back in the 60s or 70s. There's a famous paper by one of the most important theoretical ecologists, Robert May, that's called Simple Dynamics with Very Complicated Behavior. Okay, so this is simple in the sense that you don't have anything stochastic or 10 equations or something, but has irregular behavior. Okay, so complex dynamics coming out from a simple model. Okay, so just let us try 4.1. I didn't actually try. Let's see what happens, just to see if this is 4.1. If you run it, it actually went to 0. Okay. Actually, it's done. The plot stops at 0. It gets negative value actually. Okay, so it has no sense. Okay, if I try, I can find 4.9. Crashes. Okay, so it has no sense for values over 4. Okay. Yeah, there was a question. The mic, please.
Can you repeat for me the intervals which cycle of peer 2 happens, then cycle of peer 4? So just so I can write.
So you want the values of R where you have the transition from one regime to the next one. Okay, these are called the bifurcation points. Yeah. Okay, and well, cycles of I mean, you have from 1 to 2 to 3 to R equal to 3 gives you fixed oscillations, and the 2 cycles come at 3.44949 approximately. And the point is, the next ones are getting always closer and closer. Okay, there's a ratio of the difference between one point, one R where you have a bifurcation, the next bifurcation to period 4, there's a certain interval. Then 4 to 8, there's also a simple interval, but it's smaller and smaller, and it goes on decreasing. Okay, that's a property which is characteristic of chaotic systems, and it's been discovered by Feigenbaum. And yeah, so it's easier to Google Logistic Map on Wikipedia. They have a list of the values. I can because it's really dependent on very small changes of parameter. Yeah, the mic.
So I was wondering if these examples with the curve that changes in this kind of chaotic way, if they have if they model anything in biology, in ecology.
That's a good question, and we can discuss it more extensively tomorrow, because we have only 3 minutes left. But that's a little bit more or less a matter of opinion, because also what you have is that your measurements have errors, and you will never know exactly if you had a cycle that is actually a cycle of period 2 or 3 or 4 and so on, or is it a chaotic orbit. So that's the point about these things are very subtle. And if you have measurement errors, and it's very normal to have this in the field, then you cannot know actually. But people have shown to exist chaotic behavior in the lab with usually with flies. Okay? But this is relevant to population dynamics, but it may be what happens in the lab is not relevant for what happens in the field, because you are under perturbations. And in the lab, in order to have a chaotic perturbation, you have generations and generations of people do this with blowflies and so on. And then you would like to manipulate R. But how do you manipulate R? R is connected from one generation to the next. But when you are in the lab, you can manipulate R. You can increase or decrease R. Okay, so you can decrease by just taking some of the eggs and pop out, so that you are decreasing R. You can increase R by putting new eggs and so on. So it's a little bit driven. And this has chaotic behavior. But you are more or less engineering the chaotic behavior by your tricks in the lab. Okay? So there is, but actually there's a big question, but most of the populations that you see in the field are not chaotic. Okay? So why? Maybe there could be natural selection or evolution behind, because maybe chaotic populations could have could have an effective fitness that's just smaller or something, the individuals. So who knows exactly? Okay. So there is this is a point that has been discussed a lot, and the reason I'm talking about this here is that every course on population dynamics shows you the discrete time, and so it's in order to have a more complete course, I decided to put this. But we could go on without that, actually, because in the next classes we don't have anything chaotic, because we are not trying to. We will not go on for discrete time dynamics, which is curious, because many people, when they teach, and usually in the master's or PhD programs, population modeling and population dynamics, there are many people that think that because the continuous time involves differential calculus, it is easier to work with the discrete time, which don't have derivatives, and you don't have to solve differential equations. You have only to do the iterations on the computer. But from the biological point of view, it's much more complicated. The discrete dynamics, even if the math is a little bit simpler, than with the continuous time in all the differential equations, which model most of the time they are much more realistic than the discrete time. Okay, although discrete time does not involve solving equations and you don't need differential calculus, discrete time has this kind of things that who knows how relevant they actually are. So in this case, here, when R was smaller, you had things like fixed points, which is something that you can see, and then you had regular oscillations, which are the things that you can see in some situations in the field. Well, the chaos, I don't know. So it's very complicated dynamics from a very simple model, but who knows if this is actually not a reason to discard the model or not. Okay. So that's it for now. Thank you.